The optical storage devices, that is the second category. First category is the magnetic media, and we get to know how a CD is going to have its data onto it, and how they are being read, and what is the technology that they use to store these things, right? And later we talk about the solid state storages as well. And I told you it is the modern technology of storing the data, and all these SSDs, like the solid state disks, and pen drives, microchips, and all these things are category under the solid state storages, right? So the reason of saying that particular thing as a solid state storage, it is because it doesn't have any moving parts inside it. That is why we call it the solid state storage, right? And today we are going to talk about some concept regarding the computing, which is the parallel computing. Later, you are going to learn about how the grid computing happens, right? Now, parallel computing is one of the famous concepts that we are using these days. So it shows you how a modern processor is going to solve its matter. So like it's going to execute things inside it, right? So like now generally, what our picture is, let me take the whiteboard. Yeah, so generally the picture, Nikini, good morning. We just start the session, Dua. So we are here at the topic of parallel computing in the second lesson. It's the page number 16, right? So generally, if we take a CPU, a central processing unit, it contains a place called core. Right? So in the very first era, it has one particular core. Right? So this is the CPU. Right? We had only one particular core, so any process, when programs are executed, it creates a processes. We are going to talk about these things in the fifth lesson very in detail. So this process will be taken into the core and will execute and will give us the necessary outputs, right? So later with the technology advancement, the CPU has this ability, or like the technology advanced, to have different types of cores inside it, right? So first they had the technology to have two cores inside of one particular CPU, right? So this is core 1 and this is core 2, right? So that is why the names are like core 2 duo. Oh my God, what happened here? Right? Core, I'm sorry, a dual core kind of words were introduced. Cores dekak, okay. Dual core, right? And when they have 4 cores inside it, so they tend to say like quad core, right? Now, if you think about these mobile devices and all these things, they are very fast comparing to a computer, right? Those are having like octa-core kind of processors, right? So the, then I have to answer this call. Right. So when the processor is developed onto this particular concepts, or like not actually the concepts, these particular architectures, so the same process has the ability of running inside the CPU by dividing to pieces, right? So the same process will be executed by both the cores. So it doesn't mean like the same process is executing like the entire process is executing inside both the cores, so like duplicating it. It's like this being divided into pieces. So one piece will be executed inside this core, and the other one is going to execute in the other core. So what happens is the efficiency will increase. එක හරියට අපිට අත් දෙකක් තියෙනකොට තවත් දෙකක් හම්බුණා වගේ. ඒ නැත්නම් එක එක්කෙනෙක් කරන වැඩක් දෙන්නෙක් එකතු වෙලා කරනවා වගේ. Right? So the work is not going to change. It has the same workload, but instead of one person, now there are two people are doing the thing. So if it took 1 hour to complete the work for one particular person, if the people number comes to 2, it may like done by half an hour, or maybe definitely it will be done by less than an hour, but we can't say it's going to be like very half of it, right? Sometimes it can be finished before that. Sometimes maybe it will take something in between hour and a half an hour, right? It depends, right? So likewise, when it comes to the parallel computing, it is talking about the same thing. So like solving a problem simultaneously, or like executing the processes simultaneously is called the parallel computing, right? Now here I have given you some examples regarding that. So this illustrate when this particular execution, this particular problem is provided to the computer when it is having just one core or one CPU, actually one core, right? It may take, it may solve it up to this, from these 4 steps, right? First, this is the first step, that they are multiplying 4 into 5 into 20. And the next step, they will calculate 1 into 6 as 6. And as the next step, it will calculate 5 into 3 as 15. Then later, those things will be added and 41 will be given as the answer. So if we think each and every step consumes 1 second, this will take 4 seconds to execute, right? But what happens when the parallel computing happens? So that means here they are taking like, they are talking about with 2 cores over here, right? So 2 or like more cores. So in one step, these 3 things can be happen. So අපි හිතුවොත් ඇත්තටම හිතුවොත් they are talking about 3 processes over here with 3 processes. So calculation of 20 will be done by one core, calculation of 6 can be done by another core, and calculation of 15 can be done by another core. And the addition will be done by once these 3 things are done. So the time it takes is 2 seconds for these things. Since these calculations are done separately by separate cores, so it will take only 1 second, but there are 3 people to do that. Then the addition will be due by one of those, right? So it will reduce into 2 seconds, right? So the entire process. Now, don't misunderstand that 3 processes means 3 physical processes that you can have. As I introduce you, one physical component having 3 cores according to our example. It's cores 3. එතකොට ඒ තුනෙන් execution එක ඉක්මනට සිද්ධ වෙනවා. Yes. People, is that clear? Yes, everyone? How about it? Is that clear? Right, great. නිර්මාණ මෙතන අපි කතා කරන්නේ මෙතන එක කෝ එකක් තියෙනකොට CPU එක ඇතුලේ එක කෝ එකක්. ඒ කියන්නේ එක්සිකියුට් කරන්න එක තැනක් තියෙනකොට මේ අපිට දීලා තියෙන මෙන්න මේ ප්‍රශ්නේ සිද්ධ කරන්න මෙයා ස්ටෙප් 4 වතාවකට මේක සිද්ධ කරනවා. ඒ කියන්නේ මුලින්ම 4 වරක් 5 කියන එක මුලින් ඊට පස්සේ 1 වරක් 6 කියන එක ඊට පස්සේ 5 වරක් 3 කියන එක ඊට පස්සේ එන 20 6 15 කියන ඉලක්කම් තුන එකතු කරලා 41 හැදෙනවා. right ඒක තමයි එක කෝ එකක් තියෙනවා. ඒ කියන්නේ එක්සිකියුට් කරන්න එක තැනක් තියෙනවා නම් සිද්ධ වෙන දේ. අපිට එක්සිකියුට් කරන්න තැන් ගොඩක් තියෙනවා. මේක හැටියට අපි අරගන්නවා එක්සිකියුට් කරන තැන් 3ක් තියෙනවා කියලා. එතකොට අර ಗುಣ කිරීම තුන එකවර සිද්ධ වෙනවා. 4 වරක් 5, 6 වරක් 1, 5 වරක් 3 කියන තුන කෝස් 3ක්. දැන් 3ක් තියෙනවානේ දැන් එක්සිකියුට් කරගන්න. ඒ කෝස් 3ෙන් එක තප්පරයකදී කරනවා. ඊට පස්සේ මේක එකතු කරන එක ආයෙත් ඒ තුන් දෙනාගේ එක කෝ එකකින් සිද්ධ කරනවා. එතකොට මේ එක ස්ටෙප් එකකට යන්නේ තප්පරයයි කියලා හිතුවොත් මේ කැල්කියුලේෂන් එක තප්පර දෙකෙන් මෙතනදී ඉවරයි. කෝස් 3ක් තියෙනකොට. උඩ අවස්ථාවේදී තප්පර 4ක් අපිට ගත වෙනවා. right ඔක තමයි අපි කතා බහ කරේ. clear ද නිර්මාණ?
yes
නිර්මාණ hari right. So later we are talking about what are the even though we can see the time is being reduced or like the efficiency is increased due to this parallel computing, there are some places or like a particular term that is not always true, like that may not produce us the expected output due to of these things. Like some tasks might not be divisible or like divisible, right? So then අර කලින් වැඩේ අපිට මේක execute කරගන්න පුළුවන් උනේ. Why we had this ability to do it? Because our task can be divided into 3 parts. But if there is a task which cannot be divided, so having the multi-cores or like having the parallel computing is not resulting in increase of efficiency, because that task cannot be divided further, right? Or sometimes it says some tasks may not be able to divide equally, right? It takes time. So then තුන් දෙනෙක් ඉන්නකොට මිනිස්සු තුන් දෙනෙක් ඉන්නකොට නේද? දැන් ඔය තුන් දෙනෙක් එකම වැඩක් දුන්නොත් හිතන්න ඔබ එකම ස්පීඩ් එකෙන් වැඩ කරන තුන් දෙනෙක් ඉන්නවා කියලා. right? But මම එක්කෙනෙකුට දෙනවා පැයක් යන වැඩක්, අනිත් දෙන්නට දෙනවා පැය භාගෙ වැඩ දෙකක්. මට තියෙන වැඩේ පැය දෙකක වැඩක්. So I'm providing a task of 1 hour to one person and half an hour task to the other 2 persons. So half an hour task දෙක දීපු කෙනා half an hour වලින් ඉවරයි. So they have to wait until the 1 hour task is done. මොකද මගේ task එක ඊට වඩා සරල විදිහකට කඩා ගන්න බෑ in the practical situation, right? So it won't it will give you some increase of efficiency, but not as expected, right? And again, it is necessary to take overhead associated with splitting the task, like task up also, right? Like then එක process එකක් තියෙනකොට ඒක divide කරන්න මට වෙලාවක් ඕන වෙන්නේ නැහැ. So I just මම විතරනම් කරන්නේ, if I got the task I just start doing it, right? But when there are like more people, we have to take the task and we have to divide and allocate the things. Okay, you will do this part, you will do this part, and you will do that part, right? So the time which takes to divide is also should taken into the consideration, right? Because ඒකටත් කාලයක් යනවා. right? But single processor එකකට divide කරන්න කාලයක් යන්නේ නැහැ, right? So that kind of things should be considered when it comes to the parallel computing. But again, as a concept and as a practical in the practical execution, we can experience increase of efficiency regarding the parallel computing. ළමයි විනාඩියක් ඉන්න. All right. So that is the things regarding the parallel computing, right? So now we are going to talk about the grid computing. So which is something very same, or like which is something goes with the same concept, but again, like we use this to increase our efficiency, but in a different manner, right? So when it comes to the grid computing, it says grid computing is a distributed architecture of large number of computers connected to solve a complex problem, right? Then parallel computing some other thing that we can do is like we can divide a particular task into smaller things and ask the course to execute, or else, right? So like when it comes to the parallel computing, we can divide this task and ask this course to execute. Right, so it is P1, P2, P3, and P4. So those are the these are the processes. So I'm giving the parts into these cores to execute. So this is a CPU, right? As well as there is another situation where we are having 4 cores. We can execute different kinds of processes. We can process එක නෙවෙයි නේද? එක process එක දෙකකට තුනකට කඩන්නේ නැහැ. හැබැයි අපිට processes හතරකුත් execute කරගන්න පුළුවන්. Right? So this is a one big process. Right? So these are separate processes. Right? Or tasks. Right? But when it comes to the grid computing goes with this, with the pattern of this first one. මේ pattern එක තමයි කියන්නේ, but it is not talking about a one specific CPU. It is talking about many different CPUs, right? In other words, many different devices, right? So that is why it says grid computing is a distributed architecture of large number of computers. This is the major difference. This is a large number of computers. In the parallel computer, we are just talking about one single computer, which has the CPU divided into different cores, right? But here, large number of computers, such as a network, right? And they are working together to solve a complex problem, one complex problem, right? So that complex problem is divided into smaller parts and given to the grid. So grid together, that means all the computers together is trying to solve that particular big problem, right? So in that case, this grid need a particular computer called server, right? So server is the place which has the problem and which has the centralized position or the head office of the problem, right? And from the server, that big problem is spread all over the grid and divided into several different computers. And it is, remember, it is large in number or big in number when it comes to the number of computers, right? So all the computers which is connected to the grid is trying to solve a one big problem, right? So in the last point, it says grid computing is oftenly used to complete complicated or tedious mathematical scientific calculation, right? So those are some, yeah, rocket science kind of a things, right? So remember, in the grid computer, the critical point is the network. So the networks of computers is participating solving a one big problem. So that is what we call the grid computing, right? And some examples are given here. Application partitioning that involves breaking the problem into discrete pieces, right? Discover and scheduling the task and workflows, right? Some advanced concepts. So just read through and remember some of those, right? Because if we are going to talk about these things, it's going to be something complex for you to talk about, right? So just remember as the points, right? So when we are doing the operating system, we are talking about a component called scheduler, right? So scheduler is acting in the nature of the grid computing, right? So those schedulers will be able to do that particular thing, because in our operating system there are different kinds of schedulers, like indicating different kinds of computers in the grid computing. So they are working together as the grid computing works, right? So just remember the concept. It is one big problem spread all over the large number of computers to solve together, right? Here I have given some comparison regarding the grid computing and cloud computing, which is something additional, right? So you don't need to very much bother about this, right? Just read it through and it will be enough. So later we are going to talk about the von Neumann architecture. Now this is something important. This indicates, or this illustrates how the CPU and the other components of the computer is going to play their role, right? So people, is it clear what I'm saying, people? එළිය වහිනවා ඕගලන්ට disturb නෑ නේද මං කියන එක clearly you can have what I'm saying, right? Right, great, okay, all right, thank you. Right, now when it comes to the von Neumann architecture, as I told you, von Neumann architecture firstly introduced by a person called von Neumann, right? It's a Frenchman, as I remember, right? A mathematician. And he is the one who introduced this von Neumann architecture, saying this is the way that the computer works, right? Or this is the way that the architecture works, right? So I have shown you this von Neumann architecture, and let me illustrate this to you on the whiteboard, right? I'll show you what happens. Right now, this is the thing that the von Neumann said, right? What he was saying is, now there are programs installed into the secondary storage, like hard disks, right? So secondary storages are there, right? So from the secondary storage, once we execute the programs inside the secondary storage, the programs will be taken to the main memory, right? right? Usually we call it the RAM, right? So, yeah, right? So the program taken to the main memory, right? And there is another way that the main memory can have the programs, right? So it is the input devices, right? So these input devices like the mouse, keyboard, and all these things has the same ability to provide the data or the instruction into the main memory, right? So whatever the data which needs to be processed, first it hits the main memory, right? So from the main memory, it is given into the CPU, right? So let's take this is the CPU, right? And this CPU contains three components, Lamai, just a second. ළමයි මගේ power disconnection එකක් වුණා ඉන්න මම share කරනවා, right? So once we have the data and instruction on the main memory, it's going to send to the CPU because CPU is the one which executes the instructions, right? So to execute this instruction, it uses three different components, actually two different components. Third one is involved in a minimal time. So there is a component called registers. Registers, right? Now registers are a memory component, right? This is a memory component inside the CPU. And there is another component called the ALU. And ALU stands for arithmetic and logic unit. Right? And the very last component is called the control unit. Control unit, right? We call it the CU, right? So what actually happens is from the main memory, the data and instruction first moves into the registry memory because it is the one which can hold the instruction like a memory, right? It's a temporary storage device like the main memory. So once it receives the instruction, it is given to the ALU, right? Because arithmetic and logic unit is the one which executes the things. right? It can solve the things arithmetically, or it can solve the things logically. So those are the only things which received by the computer, either the arithmetical things or the logical things, right? So ALU do the execution, right? And remember, now main memory is getting lots of instructions into it, and main memory is careful to send the data and instruction one by one to the registers, because register memory is the smallest memory in the computer system. It is the smallest one. Main memory comparing to the register memory, it is very big, because register memories are coming from kilobytes and megabytes. Main memories are coming from gigabytes. So it's 1,000 times bigger than the register memory. Sometimes 100,000 times, right, are bigger than the register. So main memory has a lot of instructions. So one by one is given to the register memory. So once the register memory received the instruction, it quickly send it to the ALU, and ALU will execute it, and then they will give the result to the registry memory again, right? Then once the result is received by the registry memory, it is going to transfer that result to the main memory as quickly as possible, right? So the data instructions are given earlier, and the results will be given to the main memory in this manner. So once the data inside the main memory, we can save the data. Once we save it, it can be saved into the secondary storage, or else we can send these results into the output devices as well. Right? So this is what we call von Neumann architecture, right? But even though we can see these components inside the von Neumann architecture, these components are not performing their task automatically, right? That is where this control unit comes to the play, because control unit is the component which is responsible of sending the commands to each and every component of the computer system, right? So the major function of the control unit is sending the control signals to the each and every component of the computer system. Once they receive the control signal, then they know, okay, there is a task for me to do. So they know about the task, but they should receive the control signal to perform their task, right? So control unit sending the control signals to each and every component of the computer, right? So then these people will execute their work. Now that is what the von Neumann is trying to explain, right? So the dotted lines, they indicate data or instructions, and the straight lines, they are indicating signals or commands. Right? Okay. People, is that clear? Right. Okay. So the diagram is there in your handout, so you can go through. Right? It tells you the same story. Right? Okay. So yeah. So let's talk about the fetch execution cycle. Yeah, let's talk about the fetch execution cycle and then go, because fetch execution cycle is related to the von Neumann architecture, right? Now this fetch execution cycle, yeah, before we go to the fetch execution cycle, I have to tell you about this data bus and control bus. Now I told you this control entry is there to send the control signals. So to send the control signals, like on the motherboard, then මෙයාව ගිහිලා connect වෙන්නේ CPU එක connect වෙලා තියෙන motherboard එකට. So motherboard has the circuit lines to take the signals and data and instruction. So there are circuit lines which is separate to take the control signals. Those are called control buses, right? And there are some circuit lines which is allocated to take the data inside it. So those are called data buses, right? So those can be, sometimes they can be the circuit lines, or sometimes they can be wires, right? So anyway, they are taking the data. And there is another bus called address bus, right? Which responsible of delivering the address. Now, when it comes to the computer is having data, and every data is referred by an address, right? So data and address is always used when we are dealing with the data, right? Inside the computer, when they are dealing with data. So like they are transferring data from one point to another. It is the data as well as the address is being transmitted. So to transfer the data, or like to transport the data here and there, the data buses are there. To transfer or to communicate the address of a particular data, the address buses are there as well, right? So I want you to write the address bus. Regarding the address bus over here, I'll tell you what to be written. So have a small subheading called address bus. Let's write it with a very short definition, with a very short definition. So yeah, go like this. Yeah, hold on a second, people. Just give me a second. I'm searching for a proper explanation. I want to draw. You want to draw? Yes. Yeah. People, let's go like this. Address bus is talked in related to the data as well. Yeah, write it like this, people. Address bus is the subheading. It's better you write it over somewhere here. So write down an address bus is a computer bus architecture. An address bus is a computer bus architecture used to transfer data the data between devices, between Suhara. Right, sorry for that, people. So I'll read you again. An address bus is a computer bus architecture used to transfer data between devices that are identified by the hardware address. Of the physical memory. Right. An address bus is a computer bus architecture used to transfer data between devices that are identified by the hardware addresses of the physical memory. Right. Now, when it comes to the fetch execute cycle, this explains how a particular instruction are being executed. Right? What's happened to the instruction which is being taken from the memory? Right now, in the one Newman architecture, I described to you, the processors will be there in the main memory. They are stored in the secondary storage. And once they executed, they come onto the main memory. So executing programs will be there on the main memory. So that means the data related to those programs are in the main memory. So whenever the computer needs to execute something, it needs to take things from the main memory. So fetch execution cycle explains what happens to the fetched data, or like the data which is taken by the main memory. Api fetch karnawa kiyala kiyanne aragannawa kiyala meaning එක, right? So in fetch execution cycle, it simply explains. Now, when it comes to the computer architecture, this is a huge explanation, which is related to a lot of registers and all these things. But in our syllabus, we explain it in a very simple manner. So the very first thing that happens is the control unit. I told you the control unit is there. The major function is like sending the signals, command signals to the components. And this is another function of the control unit. Control unit is the one which fetch the data from the main memory. So control unit is having the data from the main memory first. Then it decodes the data. which is the fetched data, right? So decoding means like when we are like fetching the data from the main memory, it is not in the form which can be understood by the ALU. So decoding means converting the data or the instruction into an understandable form from the ALU, right? So those decoded instruction is given to the arithmetic and logic unit, right? Then the result will be stored inside the main memory again, right? So fetching the main memory from the main memory, decoding the instruction, allowing the ALU to execute, then again storing the result at the main memory, right? මේ අතරතුරේ registers උත් සම්බන්ධ වෙනවා, right? නමුත් අපි අර මේ outer picture එක නැත්නම් rough picture එක ගත්තොත් main memory එකෙන් data ගන්නවා, that means fetching, it will be decoded and it will be executed, then again stored inside the main memory as the last point. Right, so if you are asked to draw the fetch execution cycle, this is the diagram that we need to draw. ඉතින් මේක මේ විදිහටම නෙවෙයි, ඔයාට cycle එකක් විදිහට අඳින්න පුළුවන්, නේද? row එකක් විදිහට අඳින්න පුළුවන්. Anyhow, things happen on this manner: fetching, decoding, executing, and storing. Then it fetch the next instruction. Right, the instruction eking එක තමයි, as I told you, are being executed. So take an instruction, decode instruction, executing, storing, and again taking instruction, decoding instruction, executing, and storing. Right, so this is what you call fetch execution cycle. Is that clear, everyone? Okay. All right. So yeah, I'll stop the second lesson from this point. So most probably we will be able to finish the lesson by next week. Right. So now let's move to the gates lesson. Right. So in the gates lesson, we have done, we have went up to the simplification, neither. And we did some simplifications, like four questions, neither, as I remember. So today we are going to do more simplifications, right? And I told you, to do the simplifications, you need the Boolean laws to be remembered, right? And we discuss about those Boolean laws. Excuse me. Excuse me. And if I recap the things, like there were different kinds of laws regarding the Boolean algebra, right? And we talk about the associative laws, we talk about the distributive laws, we talk about the idempotent laws, identity laws, inverse laws, double inverse laws, the redundancy laws, and the De Morgan's, right? So these things are widely used on these simplifications, right? All right, so we have done up to the fourth question so far, right? And let's try from the fifth question, right? You people have to do all the 16 questions, right? So you can have a better practice regarding it. So let's continue, right? So go with the fifth one, everyone, right? And let me have the answers. I'm doing the math. Just another 3 4 minutes. It's 12:29. I'm doing this for 12:34, right? Okay. Give it a try, people. If you're done with five, go to the sixth, right? You can continue.
සර් පස්වෙනි එක ඩිස්ට්‍රිබියුටිව් එකක් දාන්න වෙන්නේ.
Oh, distributed දාන්න පුළුවන් නිර්මාණ.
සර් හත්වෙනි එක කොහොමද කරන්නේ?
හත්වෙනි එකේ ඔයාට කොමන් ටර්ම් එකක් එළියට ගන්න පුළුවන්. distributive law එකේ reverse එක.
හරි.
right?
සර් ඒක ඒ ගත්තයින් පස්සේ b.c කියලාත් නේ කියන්නේ අපි bc කියලා කෙලින්ම දාන්නද?
ඩොට් එක පාවිච්චි කරන්න.
හරි. සර් x bar.y වගේ එකක් ආපුවම අපි කොහොමද ගන්නෙ?
මොකද නිර්මාණ?
x bar.y වගේ එකක් ආවම පස්සේ කොහොමද ගන්නෙ?
x bar dot y වගේ එකක් ආවමද?
ඔව්.
ඒක පුතේ දැන් මට ඔහොම තනියෙන් කිව්වට හිතා ගන්න බෑ පුතේ. x bar dot y කියන එක තනියෙන් මුකුත් විසඳන්න කරන්න බෑ. තව දේවල් එක්ක කනෙක්ට් කරගෙන තමයි ඔයාලට කතා කරන්න වෙන්නේ. ඔයා 9 වෙනි ගාන ගැනද කතා කරන්නේ?
නෑ සර් 8 වෙනි එකේ මේ අර p bar.r කියලා දෙන එක මට සර් ඒක අර ගන්න තේරෙන්නේ නැහැ කියන්නේ. ඔතන p තිබ්බනම් මට එකක් ගත හැකියි. අර
ඔව්
වෙන
ඒ කියන්නේ මේ ඔයාලට දැන්
ටර්ම් එකක් දීලා
බැලු බැලමට දෙයක් ගන්න බෑ. ඔයාලට දැන් p වරහන් දාලා q r p bar.r තිබ්බම මුකුත් කරගන්න බෑ තමයි. ඒක එහෙම දැන් එහෙම ගන්න බැරි නම් ඔයාලට ඊළඟට තියෙනවා වරහන් සුළු කරගන්න ඔප්ෂන් එකක්. p වලින් q r කියන එක සුළු කරගන්න. ඊට පස්සේ බලන්න මොනවා හරි කරන්න පුළුවන්ද කියලා. නිතරම අපිට එකපාරට හැමදේම කරගන්න බැරි වෙනව නිර්මාණ. එක ක්‍රමයක් හරියන්නේ නැත්නම් මොකද ඔයගලන්ට හිතන්න පුළුවන් පොයින්ට්ස් තමයි පොදු පදයක් එළියට ගන්න එක. වරහන් සුළු කරගන්න එක. ඒ දෙකටම ඩිස්ට්‍රිබියුටිව් ඕන වෙන්නේ. right? එහෙම බැරි නම් ඊට පස්සේ ඩී මෝගන්ස් ඇප්ලයි කරගන්න පුළුවන්ද කියලා බලන්න පුළුවන්. ඔය පොයින්ට්ස් තමයි තියෙන්නේ. එතකොට දැන් එක පාට දෙයක් පේන්නේ නැත්නම් වරහන තියෙනවා නම් වරහන සුළු කරලා බලනවා මොනවා හරි දෙයක් කරගන්න පුළුවන්ද කියලා. right? ඒ වගේ එක එක අප්‍රෝචස් වලට යන්න වෙනවා පුතේ. Right, so I'm going to do the fifth question. Hold on a second, people. Okay, so I'm doing the fifth one. Here comes the fifth one. So it says A plus B bar dot B plus C. Right, so like I can't take anything common out. මොකද එහෙම ගන්න නම් dots වලින් බැඳිලා තියෙන්න ඕනේ මේ කට්ටිය. Right, so what I can do is I can apply the distributive law to these brackets, right? So that means A will be multiplied with these two and B bar will be multiplied with these two, right? So you can write AB, A dot B, much better, plus A dot C plus B bar dot B plus B bar dot C, right? So now what I can do is for these two, I can write a 0, right? So what is the law? It's going to be the inverse laws, right? So here what we have done, we have used the distributive law. So we have to write it always, right? So this equals x dot y plus x dot z. And next I'm going to say A dot B plus A dot C plus 0 plus B bar dot C. And that reason is B dot B bar equals 0. Right? Then I can go A dot B plus A dot C plus B bar dot C. So that reason is x plus 0 equals x. And from this point onwards, you can't do anything else, right? Because A dot B, A dot C, B bar dot C, right? If you take these two things as the common term, inside the bracket, it will be A plus B bar. It won't do any simplifying thing again, right? ඒක නිසා the C ව එළියට ගත්තට තේරුමක් නැහැ, right? So because of that, you can end the question from here, right? It won't simplify further than that. All right, if you got any corrections to do, it's time, right? So within another 3 minutes, I'm going to do the 6th question. If you got any questions, you can ask, right? No problem. All right. Is everyone done with the sixth one? Lamai? Can we discuss the sixth one? Right, okay. So here I'm doing the sixth one. So the sixth one says A plus D dot A bar plus D bar. Right, so I implement the dash as the bar. Right. So here again, we can't apply any of the rules directly, right? So we can apply, we can try with the distributive law since we have the brackets, right? So let's implement. It's A dot A bar plus A dot D bar plus D dot A bar plus D dot D bar. So again, the reason is the distributive law. X dot y plus z can be written as x dot y plus x dot z. So now we know these are equals to a 0 as well as this equals to a 0. So we can write 0 plus A dot D bar plus D dot A bar plus a 0. X dot X bar equals 0. Right? So now we can say A dot D bar plus D dot A bar is remaining. So the reason is x plus 0 equals x. So from here after, we won't be able to do any of the changes, right? So you can stay or like end your calculation from this point, right? So if you got any corrections to do, so it's a time. I'm going to do the next question by 12:56 within another 3 minutes.
So අපර ඩෑෂ් දාලා තිබ්බොත් තරදීද?
නිර්මාණ
A.D ඩෑෂ් කියලා තිබ්බොත් තරදීද?
නෑ නෑ හරි හරි මම ඩෑෂ් එක වෙනුවට තමයි බා එක පාවිච්චි කරේ.
හරි සර් මම ඩෑෂ් කියලා දාලා තිබ්බා.
Right, okay, right. Nikini, sorry, do I just see the message? Here's the question. Right. Can we discuss the seventh one? Everyone? Okay, is there anyone still doing the seventh question? All right, so I'm going to do the seventh question. People, and still if you are not getting this, like you can ask any question regarding this, right? Ahala make a practice window, right? So here comes the seventh question. So in seventh question, you got A dot B dash dot C plus A dot B dot C dash plus A dot B bar dot C bar, right? So you can take, like, you can't apply the distributive law in the forward manner, but you can apply the distributive law in the reverse manner in here, like taking the common term out, right? So the common term, as you can see, if you consider the first one, you only have one common term over here. මේවා ගැන අපි පොඩ්ඩක් සැලකිලිමත් වෙන්න ඕනේ වැඩේ කරනකොට. And if you take first two terms, you got only A as the common term. Right? But if you think about the second and the third, you can see there are two common terms. Right? ඒ වෙලාවට common terms වැඩි කෙනා තමයි එළියට ගන්න ඕනේ. Right? In the second and third, you got A and C bar, here A and C bar. Now, when can we take the common terms out? When all the terms are bind with a dot like this. Right? So, what we are doing here is, I'm just keeping the A dot B bar dot C as it is. And plus I'm taking A dot C bar or C dash as the common term, then B plus B bar will be in the brackets, right? So the reason is going to be what? The same reason, x dot y plus z equals x dot y plus x dot z. Right? And
sir,
so, oh Nirvana.
sir, I අපිට සර් දැන් මෙතන තුනේම common terms ඒනේ තියෙන අපිට ඒක ගන්න පුළුවන්. මම ඒ
Oh,
විදිහට අරන්
පුළුවන්. No problem, no problem. ඒ වෙලියට අරගෙන ඊට පස්සේ ඇතුළේදී තනි කරන්නත් පුළුවන්. එහෙම යන්නත් පුළුවන්. කිසි ප්‍රශ්නයක් නැහැ.
හරි.
Right? So now I can say A dot B bar dot C plus, now this is going to become 1. So A dot C bar dot 1. Right? So that is the inverse law, x plus x bar equals 1. Right? Then we can go with the x dot 1 equals 1 law, right? To indicate A dot B bar dot C plus A dot C bar. Right? So the third step is going to be A dot B bar dot C plus A dot C bar, saying x dot 1 equals x. And now we have A as the common term from these two. So I'm taking A out. I've got B bar dot C plus C bar inside. Right? So for this, I can write the same law. So x dot y plus x dot z. Right? So then මෙතනින් එහා පැත්තට පෙවුනේ නැත්තම් පේන්නේ නැති තැනක් තමයි තියෙන්නේ. Right? So can you apply anything to the bracket, people? Can you apply anything to the bracket? Any suggestions? People who have done the 7th question, can we apply anything to this bracket? Yes. I'm going to write this in this particular manner. Just see, C bar plus B bar dot, I'm sorry. C bar plus, I'm going to say C dot B bar. And what is the law that I am using to do this? We can use this law. X plus Y can be written as Y plus X, right? As well as X dot Y can be written as Y dot X. Right? Bang C bar wa isarahin tiara.
කමියුනිකේටිව් ගන්න.
මොකද පුතේ?
කමියුනිකේටිව්
Oh, commutative law. Oh. Right? So mang C bar wa isarahata aragena B bar dot C wa පිටිපස්සෙන් තිබ්බා. තියලා B bar dot C කියන එක්කෙනා මාරු කරා B C dot B bar කියලා. Right? දැන් මේ වරහන ඇතුලේ තියෙනවා redundancy law එකක්. කාටද කියන්න පුළුවන් උත්තරේ? What's going to be the answer? There's a redundancy law inside this. Which redundancy law that we are going to apply and what's going to be the answer?
සර් ඒ කියන එක විතරයිනේ දෙන්නේ අපිට.
නෑ, A කියන එක විතරක් නෙවෙයි එන්නේ. A කියන එක විතරක් කෙනවා කියලා කියන්නේ
සර් ඒකට C dot C bar plus C කියලා තියෙනකොට සර් අපිට ඒක ගන්න බැරිද වෙන් කරලා ඒකට 1 එන්නේ.
කොහොමද 1 එන්නේ? ඔයා කියන්නේ මේ දෙකට 1 කියලා ගන්නද?
ඔව් සර් එහෙම ගන්න බෑනේ මල්ටිප්ලිකේෂන් එක නැහැ නේ.
බෑ. ඔව්. මොකද එයා මල්ටිප්ලිකේෂන් එකත් එක්ක බැඳිලා තියෙන්නේ. නිකිනි it's the same mistake that you have done දුව. දුව කිව්වෙත් ඒ නිසා නේද? Just look at the redundancy law. There are 4 redundancy laws.
සර් x plus x dot y equals x කියන එකද ගන්නේ?
ඒකේ nature එක මොන වගේද? First redundancy law එකේ nature එක x plus x dot y ආවම nature එක වෙන්නේ x is staying alone and the same x doing the multiplication with y. So we can write it as x. Right? ඒක තමයි එයාගේ nature එක. ඊළඟ redundancy law එක x dot x plus y, that means x is alone again, dot same x doing the plus operation with y. Still we can write this as x. The x තනියෙන් ඉන්නවා, ax වගේම කෙනෙක් dot operation එක කරනවා y එක. එහෙම නැත්නම් x තනියෙන් ඉන්නවා, ax වගේම කෙනෙක් plus operation එක කරනවා y එක. Right? අනිත් දෙන්න මොන වගේද? x plus x bar dot y. Now what is the relation? X is alone, its complement doing the dot operation with y. So we forget about the complement. That means x plus y. goes in the same way. X dot x bar plus y, x is alone, and its complement doing the plus operation with y. So this is x dot x with the operator in both the times, and we forget about the complement. So y. දැන් මේ හතර දෙනාගෙන් කවුද මෙතනට ඇප්ලයි කරන්න පුළුවන් වෙන්නේ?
සර් තුන්වෙනි එක දාන්න පුළුවන් නේද?
අන්න හරි. තුන්වෙනි එක දාන්න පුළුවන්. Very good. Because C bar is staying alone. C bar's complement. What is the C bar's complement? C double bar. C double bar means C. Right? So complemented one is going to forget. තනියෙන් ඉන්න කෙනා එහෙම ලියවෙන්න ඕනේ. Right? So you can have A over here. C bar will be remaining. මොකද තනියෙන් ඉන්න කෙනා තනියෙන් ඉන්න විදිහටම ලියවෙනවා. මේකෙත් මේ දෙන්නනේ තනියෙන් හිටියේ. ඒ දෙන්න මෙතන තනියෙන් ලියලා තියෙනවා. And the complemented one, C double bar is the complemented one. That is going to forget. So C is forgotten plus B bar is remaining. So that is the final simplified answer. තේරුණාද? ළමයි එකම දේ ඔතන pattern එක අඳුන ගන්න එක විතරයි. Right? Follow the pattern. Follow the pattern. Right. So here comes the seventh one. Right? So go on. Right. So I'll do the eighth one within another 3 minutes. Right? If you're done with 7, go for the 8th. Hari, are we done with the 8th question, people? Yes, everyone. Is there anyone still doing the 8th question? All right. So I'm going to do the 8th. Right, here we go. So the 8th question, P dot Q plus R plus P dash dot R. Yeah, so we can't we can't see any common things straight away, right? So we can see a bracket, so we can apply the distributive law. So let's apply it. P dot Q plus P dot R plus P bar dot R. So the reason is the distributive law, x dot y plus z equals x dot y plus x dot z. So now we can see something common. Where are the places? Either we can go with, oh no, there is one place, right? So like saying P is common in these two terms, it has no point because we got P as a common one because we solved this using the distributive law, right? So because of that, we have to consider either of these terms with this one, right? So the most suitable one is the second term and the third term, right? Which is P dot R and P bar dot R. So what are we going to do is, we are going to take P dot Q will stay as it is. So we are going to take R out, which gives us P plus P dash inside. So this is going to be the very same law, the distributive law, right? And we know this equals to 1. So we can say P dot Q plus R dot 1. The reason is x plus x bar dash equals 1. And then we can say P dot Q plus R is the final answer because x dot 1 equals x. Right? So that's the one which is going to be the final answer. Right? So happy corrections if you've done anything wrong. I'm going to do the 9th question within another 3 minutes. Right? So 125. I'm going to do the next question. Right? So this is the 8th.
සර්
ඔබද
එතකොට අපිට සර් මෙතන p.q plus p.r plus p bar dot r කියලා තියෙනවා සර්.
ඔව්
එතකොට මේ අපිට අර දෙක විතරද ගන්න පුළුවන් කියන්නේ p bar plus p කියන එකද තර තුනම ගන්න පුළුවන් සර් බැලු.
කොහමද තුනේම R නෑනේ නිර්මාණ.
හරි සර්. ඒ කියන්නේ කොමන්ට් ටර්ම්ස් එන්න ඕනේ දෙකම එහෙම ගන්න අපිට.
ඔව් ඔව් අපි මේ R එළියට ගන්නේ හැමතැනම ඒ කියන්නේ R තියෙන තැන් වලින්නේ. ඒතර හැමතැනම R තියෙන්න ඕනේ R එළියට ගන්න. හැමතැනම කියන්නේ අපි සලකන පදවල R තියෙන්න ඕනේ.
හරි සර්.
right?
හරි සර්. සර් ඩබල් බ්‍රැකට් තියෙද්දි කොහොමද කරන්නේ? මට 9 වෙනි එකේ
9 වෙනි එකේ එතකොට මුලින්ම ඇතුලේ බ්‍රැකට්ස් සොල්ව් කරගෙන ඉන්න ඕනේ. ඒ කියන්නේ ඔයාගේ තියෙන්නේ x y වල ටෝටල් බාර් එකක් තියෙනවා. ඊට පස්සේ ප්ලස් ස්ක්වයර් බ්‍රැකට් දාලා x_y.x.y බාර් තියෙනවනේ. එතකොට ඒ අර ස්ක්වයර් බ්‍රැකට් එකයි මුලින්ම තියෙන බ්‍රැකට්ස් දෙකයි. ඒ කියන්නේ x + y වල ටෝටල් බාර් එක කියලා තියෙන බ්‍රැකට් එකයි ඒ දෙක එක ලෙවල් එකේ තියෙනවා. හරි. ඒ කියන්නේ මෙයයි මේ ලොකු බ්‍රැකට් එකයි එකම ලෙවල් එකේ. මේ දෙන්න ඉන්නේ ඊට
ඔතනත් කොමන් ටර්ම්ස් ගන්න පුළුවන් නේද අපිට?
මොකද පුතේ?
ඔතනත් කොමන් ටර්ම්ස් ගන්න පුළුවන් නේද?
බෑනේ කොහොමද කොමන් ටර්ම්ස් ගන්න මෙතන?
x කියන එක ගන්න පුළුවන් නේ?
බෑනේ. ඇයි මෙතන ප්ලස් එකක ඉන්නේ බැඳිලා තියෙන්නේ. ප්ලස් වලින් බැඳිලා තියෙනකොට අපිට කොමන් ටර්ම්ස් ගන්න බෑ. right? එතකොට ඩිස්ට්‍රිබියුටිව් දාන්නම වෙනවා. Right. Are you done with the 9th question? Is there anyone still doing the 9th question? All right, people. Okay, you'll try the questions from the 9th, right? So we are going to continue in doing the calculations. I think you are getting into things now, right? දැන් පොඩි පොඩි තැන් වල තමයි ඔයගොල්ලෝ හිර වෙවි යන්නේ, right? So you try the ninth one. මම ninth එක ලියාගෙන නැති ninth එක ඉවරයි ඉන්නවා නම් 10th ලියා ගන්න. Right? So if you got a chance, just if you can write down the things, just write down all the question. That will be much easier for you to try. So if you got a chance at home, so just give it a try. Doesn't matter. Right? So anyway, I'm going to continue doing these maths from next week onwards as well. Right? So you have to be good at this. Right? Idea එක එන්න ඕනේ. මොන තැනද වැඩි කරන්නේ, මොන තැනින්ද පොදුපද එළියට ගන්නෙ. Right? So for that we need to do the practicing. That is why we are doing this. Right? So write down the rest of the questions, right, if you want. Anyway, just try the ninth one, ninth and the 10th. 9යි 10යි ලියා ගන්න අනිවාර්යෙන් ඒ දෙන ගෙදරදී try කරන්න. Right?
බා දෙක ආපුවම කොහොමද x bar plus x bar කියලා?
x bar dot x bar.
නෑ සර් plus එක.
මට පැහැදිලි නෑ නිර්මාණ අහන එක.
ඔව් සර් මේ x bar dot dot එක තියෙන්නේ. ඒකේ bars දෙකක් එක තැන ආපුවම මොකද වෙන්නේ කියලා හෙව්වා.
ඒ කියන්නේ x bar dot x bar ද?
ඔව්.
බලන්න ඕකේ තියර එකක් තියෙනවා අපේ මේ ඇතුලේ. idempotent law එක පොඩ්ඩක් ගිහිල්ලා බලන්න. idempotent law එකේ තියෙනවා අපි හතරක්. Right? So people, please write down the 9th and the 10th. You have to try the 9th and the 10th at home. And if you want, you can write the rest of the things, right? Anyway, I'm going to do those things, right, in the next week as well, right? So keep it up, people. I'm going to meet you on next week for the very same time, right? Until then, have a nice weekend, right? So I'm going to end the session from here. And I'll leave this until every one of you are exiting the session, right? Okay. Thank you very much, everyone. Right? Okay, people.
Sir, ये open किया मैंने
මොකද්ද නිර්මාණ?
Sir, ये set are ये हुए.
නිර්මාණ. ඔව් ඒ ටික බලන්න. ඔයා මට ඊයේ කළේ වගේ. Right. නිර්මාණය කීවෙනි ප්‍රශ්නේ ඉඳලාද?
Sir, 28 29 30 31 32.
හරි. 28. මේ ටික අපි ඊයේ කතා කරේ නැද්ද?
නෑ සර් වැඩ කියලා කිව්වා.
නෑ
ඊයේ සතියේ දුන්නේ සර් හදන්න.
ඊයේ සතියේ
කතා කරේ නෑ සර්.
අපි කතා කරේ නෑ නේ.
නෑ කතා කරේ නෑ.
Yes. Right, okay, select average hours from student underscore teacher, select average hours. Oh, put a make a ඒගොල්ලෝ කියන්නේ find the total fee. Total fee එක නෑ 27 නේ. මෙතන find the average number of hours of teaching session. අපිට කියන මම මේ session එක record වෙන එක නතර කරලා ඉන්න නැත්නම් මේකත් record වෙනවා.